Hi everyone, this is Mrs. GA, and today we're going to be finding rational solutions of polynomial equations. So I have a quick warm-up for you guys, so please pause the video and give this a try, and when you're ready, hit play to check your answers. Okay, go ahead and check your work here. So remember, to determine if something is a factor, we can use synthetic division. So if x minus 2 is the factor, we use positive 2 here. So imagine you're using the 0. You do your synthetic division, and what you're looking for is a remainder of 0. So since this does have a remainder of 0, it means that x minus 2 is a factor. So you take the remaining polynomial, which in this case is 4x to the fourth plus 0x cubed minus 29x squared plus 0x plus 7. So I wrote that right here. And you see if you can factor this more. In this case, we can. This is a quadratic type equation like we practiced in class earlier this unit. And you can factor it as if it said 4x squared minus 29x plus 7, and then just adjust the degree of your first term. But this does become 4x squared minus 1 times x squared minus 7. And then this you can factor even more using difference of 2 squares. So you end up with these 4 factors as your final answer. So up until this point, every polynomial we've been working with is either completely factorable by hand, or it's like in the warm-up where I give you one of the factors. So today we're going to learn, well, what do you do if you look at the polynomial and it's not factorable? Where do you start? So we're going to learn about what's called the rational root theorem. So the rational root theorem essentially gives us a list of possible rational real zeros to try that we can test using synthetic division. So this says if p of x is a polynomial function with integer coefficients and p of x has at least one real rational zero. Now this is important because not all polynomials have real rational zeros. So some polynomials don't have any real zeros, so you could try this process and it still wouldn't work. But if it does have a real rational zero, then one of those zeros, or at least one of them, will be in the form of m over n, where m is a factor of your constant term. Remember, the constant term is the term without the variable, and n is a factor of your lead coefficient. So what does this mean? You essentially look at your constant term and you list out all of the possible factors of that value, and then you look at your lead coefficient and you list out all the possible factors of that value, and then you create all of the possible combinations of m over n, and that gives you a list to try. So sometimes you end up with a list of 6 terms to try, sometimes you end up with a list of 24 terms to try. It just depends on the combination of numbers. So when we're using the rational root theorem, here's the process you take. Again, always check to see if you can factor your polynomial by hand, but if you cannot, you're going to list out the possible real zeros using that rational root theorem. So you list them all out, and then you just start testing them using synthetic division. And again, just like in the warm-up, we're looking for a remainder of 0. Once you find a 0 that works, you can look at your remaining expression and try to factor it more by hand. And if you can't factor by hand, then you look at that remaining expression and you start all over again doing the rational root theorem again until you have factored your polynomial as much as you possibly can. Okay, let's give one of these a try. So if you look at this polynomial, this is not something we can factor by hand. Like you could try factor by grouping, but it won't work. So we need to use the rational root theorem to give us a list of possible zeros that we can try. So remember, we're going to do all the combinations of m over n. So m is are the possible factors of negative 20. So all of these, of course, there's a positive and a negative. So the factors of negative 20 would be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and plus or minus 20. So those are all of the possible factors of negative 20. So remember, factors are just numbers you can divide in evenly to another number. And then we're going to list out all of the possible n values, which are the possible factors of your leading coefficient, which in this case is 1. So our only possibility for that is just plus or minus 1. So all of our possible zeros, so we list out all the possibilities, the possible combinations of m over n, would be plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 4 over 1, plus or minus 5 over 1, plus or minus 10 over 1, and plus or minus 20 over 1. So here we actually have 12 possible rational real zeros to try. So unfortunately from here, our only option is really to just start testing the different options using synthetic division, and you keep trying until you get one that has a remainder of 0. So for these, since we're going to be testing a lot of different numbers, and you might actually test maybe 3 or 4 or 5 before you even find one that works, I'm going to set it up a little differently just to kind of make it a little more efficient. So along the top, I'm going to list out my coefficients for my polynomial. So I'm going to list out 1, 2, negative 19, and negative 20. And then along the side, I'm going to list out the zeros that I'm going to try. And I'm going to kind of skip that middle row of synthetic division. So we know that we multiply by our box number and then we add vertically. So I'm going to see if we can do that step in our head. So let's just start by trying the 0, positive 1. That's a good place to start, but really you can start wherever you want. So remember, for synthetic division, you just drop down the first term, so it will always be a 1 here. Then you take this number, you multiply it by your box number. So 1 times 1 is 1, and you add it to 2. So we get 3. 1 times 3 is 3, and you add it to negative 19, so we get negative 16. 1 times negative 16 is negative 16. Add it to negative 20, and we get negative 36. So this last column of numbers right here, this is going to be our remainder. So in this case, we get a remainder of negative 36. So we know that positive 1 is not one of our zeros. So then we just have to try something else. I don't know, let's try positive 2, and let's see if that works. So again, drop down your first number. 2 times 1 plus 2 is 4. 2 times 4 plus negative 19 is negative 11. And then 2 times negative 11 plus negative 20 gives us negative 42. So again, our remainder is not 0, so that means that 2 doesn't work. Let's try, I don't know, let's try positive 4. So you drop down your first number and you get 1. 4 times 1 plus 2 is 6. 4 times 6 plus negative 19 is 5. And then 4 times 5 is 20. Plus negative 20 is 0. So we have found a zero that works because the remainder is 0. So that means that our first factor is x minus 4. So remember, when you're testing the number in your box is your 0. So the factor is always going to be the opposite of that. And then let's look at our remaining polynomial. So remember, our original degree was 3, so our answer, or what's left over, will have a degree of 2. So it's x squared plus 6x plus 5. And then we just look at this and say, can we factor more? And you absolutely can. So we get x minus 4 times x plus 5 times x plus 1. So here is the factored form of our polynomial. And now we can use that to find all the zeros. So if you did zero product property, you'd get x equals 4, negative 5, and negative 1. So those would be our solutions. So you can see that this process of using the rational root theorem, it can be a little bit tedious. It's really kind of a matter of luck sometimes for how quickly you find a zero that works. But if you look here, we could have tested 4, negative 5, or negative 1, and any of those would have given us a starting place, and then our remaining trinomial would have been factorable from there. Okay, let's try one more together. So again, this is not factorable by hand right now. I mean, it has 5 terms, so we don't even really have a technique for factoring this unless there's a GCF. So we're going to need to use that rational root theorem. So if you think about all of the factors of m over all of the factors of n, here again our leading coefficient is just 1. So it's going to be all of these factors over 1. So that gives us possible zeros of plus or minus 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, 8 over 1, 12 over 1, and 24 over 1. And all of these our plus or minus. So you can see here that we have 16 possible zeros to test. So again, from here, it's just a matter of plugging through with synthetic division until we find one that works. So let's start by setting up our little chart really quick. So I'm going to list out my coefficients. So 1, -4, -7, 22, and 24. And then here we can list out our zeros that we're going to test. And remember, this last column will represent our remainder. So we want our remainder to be 0 here. So let's test +1. Let's start with +1. So drop your first number. 1 times 1 plus -4 is -3. 1 times -3 plus -7 is -10. 1 times -10 plus 22 is 12. And then 12 plus 24 is 36. So 1 is not one of our zeros. Okay, let's try 2. You don't have to go in order. You can try whichever ones you want. So drop this down. 2 times 1 plus -4 is -2. 2 times -2 plus -7 is -11. Here we have -22 plus 22, which is 0. And then here we have 0 plus 24, which is 24. So 2 is not one of our solutions. Okay, let's try 3. So drop your first number. 3 plus -4 gives us -1. -3 plus -7 gives us -10. Then 30 plus 22 gives us -8. And then here, -24 plus 24 gives us 0. So we have found one of our zeros. One of our zeros is +3. So that means the factor would be x minus 3. And then let's look at our remaining polynomial. Our remaining polynomial is x cubed minus x squared minus 10x minus 8. So this remaining polynomial, you could try to factor it using grouping, but you'd find pretty quickly that it doesn't work. So when you get something like this, and it's not factorable, unfortunately, that means that we have to start all over again with the rational root theorem, except we're going to be doing it with this smaller polynomial. So it does reduce down our possible zeros. So let's list out our possible zeros for this remaining polynomial. So our m value is -8, our n value is 1. So it's all of the factors of -8 over 1. So we have plus or minus 1, 2, 4, and 8. And again, all of these are plus or minus. So it gives us 8 possibilities to try. So hopefully it won't take us quite as long to find one of our answers. So let's again set up our chart. And I'm just going to use the coefficients of this smaller polynomial, not my original one. So we have 1, -1, -10, and -8. And then remembering that this last column is going to represent our remainder. So I don't know, let's try again. Let's start with just +1. And again, you can start with any number you want. You can start with a negative number. It doesn't matter. Whatever seems like is a good choice to you is what you should do. So drop down your front number, and then 1 times 1 plus -1 is 0. 1 times 0 plus -10 is -10. Here, -10 plus -8 is -18. So 1 didn't end up working, but that's okay. Let's try, I don't know, -1. So drop down your first number. Here, -1 plus -1 is -2. 2 plus -10 is -8. And here, +8 plus -8 is 0. So that means that -1 is one of our zeros, because again, the remainder is 0. So that means that our next factor is x plus 1. So remember, this is the 0, so our factor is the opposite. So we have the factor of x minus 3 from what we found up above, and then the next factor we found was x plus 1 from this row. And then let's look at our remaining polynomial. So our remaining polynomial would be this, starting with x squared. So x squared minus 2x minus 8. And then we just look at that trinomial. As soon as you get down to a trinomial or any quadratic, we should be able to finish factoring or solving from there. So even if it's not factorable, we could always finish solving using the quadratic equation. But this one is factorable, so let's finish factoring that trinomial. So x minus 3 times x plus 1 times x minus 4 times x plus 2. So that's our factored polynomial. So that gives us 4 zeros, it gives us the zeros, positive 3, negative 1, 4, and negative 2. And there you have it. So again, if you're ever doing this rational root theorem and you find as one of your factors, but the remaining polynomial is not yet factorable, you have to start over again. But you can use that smaller polynomial to find the remaining factors. All right, at this point, I'm going to ask you to pause the video so you can give this one a try on your own. And when you're ready, you can hit play to check your work. All right, go ahead and check your work here. So for this one, the possible real rational zeros are plus or minus 1, 3, 5, or 15, and it's positive and negative for all 4 of those. So you can test them out. One of them that will eventually work is positive 3, giving you the factor of x minus 3 and a remaining polynomial of x squared plus 6x plus 5, which you can finish factoring by hand. So here are your factored here's your factored polynomial, and your solutions would be x equals positive 3, negative 5, and negative 1. All right, so now that we know how to solve polynomials using this rational root theorem, let's try a word problem. So it says a company is designing a box for their product, which is in the shape of a rectangular pyramid. The base width, so this dimension, is 1 inch shorter than the base length, and the height of the box is 3 inches taller than 3 times the base length. The volume of the box must be 6 cubic inches, so what should the dimensions be? And here's just a little reminder of how you find the volume of a rectangular pyramid. It's just 1/3 times the length times the width times the height. So let's see if we can find a way to describe the 3 dimensions in terms of each other. So I'm going to define x as the length of the box. And I'm going to be very specific in this and even put the units so we remember what units we're working with. So this says the base width is 1 inch shorter than the base length. That means that we can define the width as x minus 1. So this is the width of the base, so this dimension right here. And then it says the height of the box is 3 inches taller than 3 times the base length. So we could say 3x plus 3 equals the height of the box. So here we have the 3 dimensions we need to model the volume. So the volume in terms of x, which is the length of the box, will be 1/3 times the length, which is x, times the width, which is x minus 1, times the height, which is 3x plus 3. Okay, so now that we have our model for the volume of this box, we know that the volume of the box must be 6 cubic inches. So we could set this equal to 6. And then to solve this equation by hand, we will need to multiply this out and set our equation equal to 0, so subtract 6. So when you do that, we will get 0 equals x cubed minus x minus 6. And again, that's just multiplying out the right side and then setting our equation equal to 0. So this, I mean, you could try to factor it by hand, but you'll see that you aren't able to. I do want to point out that this is not a quadratic type equation, so you can't factor it like a quadratic equation. So we do need to, in this case, use our rational root theorem to help us narrow down our options of what to try. So in this case, our possible zeros would be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So you can start wherever you like. I'll start by trying, I'll start by listing out my coefficients. So 1, 0, remember you do need this placeholder for your x squared term, negative 1 and negative 6. And then let's just start by trying positive 2. Here you can also guess that you should probably start with the positive zeros because this is an application-based problem and we don't want any negative lengths. So let's start with all the positive options. So drop your 1, 2 plus 0 is 2, 4 plus negative 1 is 3, and 6 plus negative 6 is 0. So this does have a remainder of 0, which means that it is a 0. So we could write it out the factored form like this. We could say x minus 2. Remember, if the 0 is positive, the factor will have a negative. And then our remaining polynomial is x squared plus 2x plus 3, which we can finish factoring by hand. So this one, once you finish factoring it by hand, and again, we are solving for x, so it's equal to 0. If you did zero product property, you would only get one positive solution. We don't want the negative solutions in this case because, again, it wouldn't make sense for the length of our box to be negative 3 or negative 1. So it looks like our only possible solution here is positive 2. So x is positive 2. So when it asks what are the dimensions of our box, we need to look back to how we defined each of our dimensions. So that means that the length of our box is 2 inches. The width of our box is going to be 1 inch because it's going to be 1 less than the length. And then the height of our box should be 9 inches, which is double the length plus 3. And here is our answer. Okay, here is the last example for you guys to try. So please pause the video and give it a try, and when you're ready, hit play so you can check your work. Okay, go ahead and check your work here. So here's the setup, and here's our model for the volume of this box. So x times x minus 2 times x plus 3. We'll set it equal to 56 because that is the required volume of the box. And then we can multiply this out and set our equation equal to 0. So this equation, or this polynomial, actually has quite a few possible real rational zeros. So you might need to plug through a few to find one to start. But the 0 of positive 4 gives us a remainder of 0. And then this remaining trinomial, be careful, it's x squared plus 5x plus 14. This is actually not factorable, and actually this gives you 2 imaginary zeros. So I know it looks kind of close to something that's factorable, but it's actually not. So this polynomial right here actually has one real 0, and that only real 0 is positive 4. So the length of our box is 4 inches, the width is 2, and the height is 7. Okay, that is all for today's video. Thank you so much for watching.